Hi everyone, my name is Julie Rosati and I'm going to be doing most of the webinar today. I also have Ashley Fry and Mitch Brown from the SERP on the phone to help with questions, and if you have any logistical problems, we can try to help with that also. If you are in the AT&T webinar and you have a logistical problem and you'd like to let Ashley or Mitch know, go ahead and send a chat note to them and they can try to help you. And we'll be stopping at certain points in the presentation for questions. So please keep your questions coming and feel free to interrupt at any time. I sent you all, or you saw the URL to get to the Sediment Budget Calculator. It's a little bit difficult to remember. It's a lot of numbers. So if you ever forget, all you need to do is go to the SERP website, which is serp.uspace.army.mil, and then you go to Products, and then Sediment Budget Tools, and then it's the second tab under the Sediment Budget Tools, and there's the link right there if you ever need to get it. Also, our tech note on the calculator, which we're going to be following today, if you need a copy of that, it's right here posted on the website. And there is one correction that I'm not sure has been posted up to the website yet, but the version I sent you yesterday is that supersedes. It's got some red marks in it, so if you have the red marks, you've got the right version of that tech note. And that'll be published in a few weeks, hopefully. So we'll go ahead and get started with the calculator. But before we do that, I'd like to have Ashley give just kind of an overview of what we're doing in development of sediment budget tools in the SERP. We have a number of things going on in conjunction with the Regional Sediment Management Program. So I'll let Ashley kind of have a little introduction here.
Thanks, Julie. My name is Ashley Fry, and before Julie goes into more detail about the Sediment Budget Calculator, I just want to take a couple of minutes to discuss some of our ongoing work and then also talk about our philosophy on sediment budgets. So the reason I want to bring all this up is because there's been some confusion about the Sediment Budget Calculator, which Julie is going to discuss today, and the Sediment Budget Analysis System, otherwise known as SBAS. Since these names sound very similar, there was some confusion as to why we could possibly have two tools that could be very similar and possibly be duplicating effort. These tools are different, and I just want to explain a little bit about what each one does and then how possibly in the future they could relate to each other. The SBAS is a tool that was developed in the late 1990s as a PC tool. And it was developed to provide a framework for formulating, documenting, and calculating sediment budgets. I think of it as more of a visualization tool. What it does is allows users to draw sediment budget cells and then fluxes into and out of those cells. And then it also allows for sand placement and removals in those cells, so you could input that information. Another possibility is to combine all the cells into a macro budget or include uncertainties or confidence levels of those sediment budget quantities. So this is basically a tally of sediment gains and losses and a series of cells over a given period of time. The only calculation in SBAS is for cell balances, and this is based on a conservation of volume equation. That's the sum of fluxes, source fluxes, sink fluxes. It includes volume change, placement, and removal. This equals the residual for a balanced cell, this is 0. Once the sediment budget is complete, then the user can visualize the sediment transport magnitudes and pathways over a given period of time. In addition to the PC version, we also have a version of SBAS in ArcGIS 10. It's available as an add-in, and it includes all the features of the PC version. And they're relatable to each other. You can pull your Arc version into the PC version and the other way around. To explain some of an application of the SBAS, one of the things we're working on right now is a conceptual regional sediment budget for Maine to Virginia as part of its post-Sandy effort. We've been compiling existing sediment budgets across that region And then as we do that, we've been inputting the information into SBAS. While we completed the work in the PC and the ARC versions, we wanted to have an easy way for others to actually view our sediment budgets. So we've been working with Mobile, and they've been developing a geoportal, which would allow users to see all the budgets at once. Because right now we have several different people working on this, and we have different regions, what we consider regions, that each person has worked on. So we have many different budgets, and they're not relatable to each other. You have to open each one separately. So it's really nice to have the geoportal where one can view all the sediment budgets at one time. It's also nice because you can view different layers and see volumes, residual removals, placements, and confidence levels. And these are all color-coded. The next step that we have is to improve the ARC version and then also begin allowing others to upload their sediment budgets onto the portal. So the SBAS, just in general, is a visualization of what the user is already inputting. On the other hand, we have the Sediment Budget Calculator, which is an online web tool that calculates a family of viable solutions for an adjacent beach and inlet sediment budget, given site-specific parameters defined by the user. And it applies the Budge method. Julie's going to go through this in more detail, but the Sediment Budget Calculator calculates multiple solutions for a sediment budget, as opposed to the SBAS, which calculates volumes and residual based on the user input. You'll notice in the CAPTN that Julie handed out to you before this webinar is that the Sediment Budget Calculator produces spaghetti line drawings of sediment pathways. Eventually what we'd like to do is connect that to the SBAS so that we can eventually have cells and fluxes from the Sediment Budget Calculator in the SBAS. Then we'd be able to complete an SBAS sediment budget for cells outside of just the inlet and the adjacent beaches. So that's just a brief overview of the SBAS and the Sediment Budget Calculator. So I'm going to turn it back over to Julie so she can go into the Sediment Budget Calculator discussion and demo.
Yeah, thanks, Ashley. That's very good. And so what we kind of see is as Ashley has mentioned, we see these tools working hand in hand. So as we go through the calculator, you'll see that you have almost 1,000 solutions that are generated, and you pick some of those to represent your inlet and adjacent beaches. And then from there, that could go into an SBAS kind of format, but that is not included in this tool yet. But they could be put together in the future. So with that, we'll go ahead and get started with the calculator. Once again, if you want to follow along, you can go to the SERP website, which is serp.usace.army.mil, go under Products, and then look at the Sediment Budget tool. And the link is there, and the example we're going to be going through is in the tech note that's right here. On the opening page of the site, there's 3 tabs that you can get more information. One is just about the Budge method, which is a way to develop these families of solutions, and it's described in the Coastal Engineering Manual Part 5-6. The second button has a link to the CEM if you would like to download it and look for more information about the Budge method. We're not going to go through a lot of the details of the method, but we're rather going to be talking about the tool and how the tool works. And then on the right side of that opening screen is an image that we're going to spend a little bit of time on. You can get, if you want, you can get more information about the terminology. This is also in the tech note, and then a larger picture. I'm not going to use this larger picture because part of it's off the page. I'm going to try to talk from the smaller version of it right now. We'll spend a little bit of time on this to make sure that everyone understands some of the definitions of these terms. So first of all, this is for an inlet system, so it's the adjacent beaches associated with an inlet. And the convention is that we talk about the right and the left shorelines and the right and the left beaches. And the convention is it is reference to a person standing on the beach that's looking offshore. So in this case, our left beach is the top part of the screen, and the right beach is the bottom part of the screen. The other thing that to keep in mind is that the direction of the arrows indicates positive values. So all these values that are shown here will be are positively directioned. If you have a net transport and the direction from top to bottom in the figure, that would be positive. If you had a net transport from the bottom to the top, that would be a negative value. The L values are referenced to a negative. So we're going to talk about a few more of the terms in here and what you do in the calculator. The way the calculator is set up is you specify a range of right and left directed transport rates at the boundaries of your study. So this could go way far away from your inlet, and you would specify the R's and the L's associated with that part of the beach. And they'll be different for the top and the bottom of your study area, or the right and the left, depending on which solution you choose. But when we set them up to be exactly the same range and increment. And you'll see us do that. And then I wanted to mention a few of the other parameters here. You will specify J values. The 1s represent the left shoreline, and the 2s represent the right shoreline. Again, remember, you're a seaward looking observer standing on the beach. And the J represents a value from 0 to 1 that represents how effective your jetties are. So if you had no jetties at this inlet, your J values would be 0. And if you had perfectly impermeable jetties that did not let sand go around them or through them or over them, then your J would be a value of 1. Similarly, the M value ranges from 0 to 1. And that represents the amount of inlet-induced transport in the very vicinity of the inlet. And it's a little bit more difficult to estimate as compared to the J value. The way I have used the M values in the past is by looking at the morphology at the inlet. If I have an inlet with a large F-shoal complex that wraps around, and I know there's some reversals perhaps on my right beach here, I'm showing with my cursor if you can see. So if the F-shoal wrapped around, and I know I have some reversals there, my M value would be higher for my right beach as opposed to my left beach. And that's kind of how we've been using the M values in our analyses. We also have gone through different calculations with different M values to look at the sensitivity of the budget and the solution to that value. We also have the opportunity to identify an upland source of sediment from a river or perhaps from erosion of a bay shoreline or even from the flood shore coming into your inlet system. And finally, the dredging and placement operations over here on the B part of this figure. You can specify dredging and placement on the left beach or on the right shore. Now, if you dredged the right beach and placed it on the left shoreline, then this number would be entered as a negative value. So this kind of gives you an overview of some of the terms and the parameters that we'll be working with. There are this p-value here, it's calculated by the software, so you don't have to enter that. But that value stands for the fraction of natural bypassing that occurs. The P1 is from the left beach into the inlet, and the P2 is from the right beach into the inlet. And like I said, the software calculates that for you. I'm going to pause right here just in case anyone has any questions about the terms or the figures that we've talked through. Okay, well, we'll go ahead and go on. So we're going to scroll down a little bit into the web page, and there's 3 tabs at the upper middle part of the Sediment Budget Calculator page. We're going to be going to the Data Input tab first, and then we'll go and narrow our family of solutions, and then we will formulate a traditional sediment budget. So that's kind of how we're going to go through it. I'm going to pause at the bottom of this Data Input tab in case anybody has any questions at that time. Okay, so I'm going to move down just a little bit more now. I wanted to point out before we get too far into it that one of the first things you should do is identify which shoreline is downdrift or of a less certain volume change. And downdrift means that you know the direction of your net transport, and it's usually the beach that is eroding more on a given section of coast. And we're going to say that our right shoreline is the downdrift shoreline for this example. If you don't have a real strong net transport, or you may not know, maybe it changes from year to year, which direction of transport is dominant, and you're looking at a 10-year period, well, then you would just choose the shoreline that is of less certain volume change. You have more unknowns associated with that beach as your downdrift beach. And the calculations will go through. Then you can also choose your units here as cubic yards per year or cubic meters per year. So what we're going to do now is enter some values up here, and we enter the minimum and the maximum range of transport rates that we would like to generate this family of solutions, as well as the increment. If you ever want to just look at a sample, you could always click on this populate sample, and it will fill in everything here for you, and you could do a quick calculation just to kind of see what it would look like. So we're going to go ahead and populate based on the data that's in the tech note. And so at the top of page 3, if you're following along, we put in 100,000 as our minimum, 500,000 as our maximum, and the increment is 50,000. And I'll pause right there in case anybody is entering data too into their spreadsheet or their website. And so once you get your values in there, you can click populate, and you'll see it'll fill out all the R1 minimum, maximum, and the increment. I apologize right here. We have a wraparound problem. This R1 minimum should be over here on the left, and we'll get that fixed when our person is back from TDY next week who will fix that for us. One thing I wanted to mention up here, if you do an increment of a very fine increment of 10 or 20,000 cubic yards per year, you will generate a larger number of solutions, and it may take a little bit longer to do your calculations. So one way, if you wanted to get a finer increment, you could narrow your minimum and maximum, and you wouldn't have so many solutions generated. Okay, so I'm going to move down a little bit. So we need to enter now the volume change on our left beach. Remember, that was the beach on the top part. And if you look at the bottom of page 3 now, our change in volume over whatever time period we were looking at on the left beach was erosion of 100,000 cubic yards per year. And typically for a sediment budget, that's at least a 5 to 10 year period to look at data. And on the right beach, it was 300,000 cubic yards per year. So you can tell that right beach is the more erosive of the beaches. And then the gross transport, I'm going to talk about that in just a minute, but we're going to put 250,000 in there for the gross transport. And I'm going to go back up to that figure and talk about the gross transport for just a second. What that indicates is the amount of sediment that this whole inlet system has captured over the time period that you're looking at, including the ebb shoal, the channel, and the flood shoal. So it's all those features that it represents. The total inlet sink is another way of talking about it. How much does this inlet take from the literal system? I didn't need to click on that. I meant to exit out. So we'll go back down here. So those are the values we entered in. For the left beach, an erosion of 100,000 cubic yards per year. The right beach, 300,000 erosion. And then the inlet has captured 250,000 cubic yards per year. And then we enter the J's and the M's and the engineering activities, the dredging and placement. And for our example, we have no jetties, so our J's are 0. And the inlet influence is looking at the morphology and the fact that there may be a reversal on the left beach. On the right beach. So I have an M2 of 0.2 and M1 of 0.2 and an M2 of 0.4. And then all the mechanical dredging and transfer of sediments for the purposes of this example are set to 0, as well as the upland source of sediment, just for simplicity here. Okay, so then we just click the calculate, and what you'll see after I click this, you'll see a little dial come over here. And this particular example doesn't take too long, and it develops a whole family of solutions related to what we entered. And I'm going to spend a little bit of time to talk about the SWOT. We're almost at the bottom of this page, and I'll take a break to let everybody ask a question if you'd like. In this plot, there's showing from the left identified by an orange triangle, showing from the right by the blue triangles, and you can see they overlay each other. And on the next tab, we can calculate the centroid and the modal solution if we want. So what this plot shows is the net natural bypassing around the inlet in cubic yards per year. The negative numbers mean it's from the left going to the, from the bottom of our figure up to the top. It's a negative bypassing, which doesn't really make sense given that our net transport is supposed to be from the top to the bottom. So those solutions don't seem too good in terms of what makes sense. But they're all viable, and they all make those equations work out. And then we have some positive values here for the net natural bypassing. On the left axis is showing from the left, and those are the orange data. And then on the right axis is showing from the right beach. You'll notice that the axes are flipped. So showing from the right, this value up here is 50,000. It corresponds to a 200,000 from the left. And similarly, the higher value of showing from the right relates to a lower from the left. And the reason for that is because the inlet's capturing 250,000, so it's related to both sides. How much does it get from both sides of the channel? Both sides of the inlet, I'm sorry. If you hover over these data points, you can see the values that are associated with each data point. So the one I have highlighted now is showing from the right, I think, and it's around 200,000 net natural bypassing, with a showing from the right of about 150,000 and a net transport of 200,000. So by kind of just looking around this figure, you can get a fairly good idea of what makes sense. For example, a net transport of 0 may not make sense for the particular inlet that you're considering. And the net transports of negative numbers would mean that they're in the opposite direction, going from the bottom of that figure to the top, which is not how we set up the problem. So probably these solutions over here with the net transport of 0 or a negative number are not viable, or not good solutions. They're all viable, but they're not the ones that we chose. And the last thing you can do here, and I'm not going to do it right now because it takes about 2 or 3 minutes to download, is you can export this data. And I saved it earlier, so let me just show you that very quickly. Where did I put it? Here it is. It saves a spreadsheet of, I'll just talk through this very quickly, of the net natural bypassing, the P value, the largest P, the showing from the left, showing from the right, the net that indicates the fraction of natural bypassing. So a P1 is on the left beach. That indicates that 60% of sediment from the left beach is bypassed around the inlet, and only 13% of sediment from the right beach is bypassed from the inlet. And with these solutions, you can look through all of them, and it's pretty apparent that not all these solutions, there's 964 of them, not all of them got plotted on this screen. And the reason for that is, I have to review a paper, sure. But the reason for that is that some of these solutions overlay each other, and the resolution of the screen is not sufficient to show all the solutions here. So I'm going to pause right now and let people ask questions if anybody has a question at this point. Okay, well, we'll go ahead and go on. So now we've entered all our work data, and if anyone has a question, you can interrupt at any time. But I will kind of take a little break at the end of each of these tabs in case anybody has any questions they're holding. The second tab, the family of solutions, this is where you can narrow those solutions. So at the bottom of this page, we see the same plot that we saw in the previous tab, but now you can narrow your solutions. The first way is to say that the net natural bypassing must be in the same direction as the net transport, which kind of makes sense. That if you're going to be bypassing sediment naturally around the inlet, you would expect that it would be in the dominant direction of the transport. and that's usually the one I click. You can also set the minimum shoreline from the left side and the maximum, and you might say, why don't you have it also shoreline from the right? Well, the reason is because they're related. So by specifying one, you can narrow it to the other one too. And you can also specify net transport range between 100,000 and 200,000. Perhaps you want to look at those solutions. And you can do multiple of these check boxes. After you check one of these, you must click Update the Chart, and it will then show you the solution. So what we said is that the bypassing P must be positive, basically is what we said. It's got to be in the same direction as the net transport. Although that looked like a negative net was there, but I don't know why that one was there. But we have mostly positive values on this page now. And you can calculate the modal solution and the centroid solution. The modal solution is the most frequently occurring solution in your data set. And if you want to double check this, you can go back to the spreadsheet and count up how many times that value occurs that is shown there. And then the centroid of the data set, which is the red one, that is about the approximate center of the solution set that you have narrowed in the previous step. Now, the coastal engineering manual recommends that the modal solution, this one here, be the value that you use for your settlement budget. However, in practice, we have used both of these solutions, and we've used several solutions to show stakeholders and our partners as ranges of likely settlement budget transport pathways in the region. So what we can do next, before we go to the next tab, you can click on any of these solutions in here and have a traditional settlement budget with the fluxes and the pathways formulated, and that will be shown on the next page. So I'm going to click on this one right here that I like, with net transport of 250,000 cubic yards per year. I should have said that net transport is for your whichever side of your inlet is the updraft side. It's that value. So for our case, in which the left beach was our updraft side, it would be the transport rate at the updraft boundary there. So I'm going to go ahead and click on that. And what that did now was take all those values that we just solved. They're all the given values that we entered, and then the selected solution that we just clicked on. And then it goes ahead and draws the settlement budget figure for you. I'll mention that you entered and also the ones that were calculated for the different queues going around the sediment, the inlet system. And then I'm going to move this plot over a little bit so you can see it better. You see the net transport on the left side, the updraft side was 250,000, and you can see that differs for the right side, the right boundary. It's greater, and you see all the transport rates that we solved for in the previous solution set. If you want to look at another solution, let's look at one with a different queue. This one, let's look at 150,000 cubic yards per year. So if I click on that one, it'll change my figure. I'm going to do this, and I'll move over just a little bit so you can see this 150,000 coming into the inlet system and 300,000 leaving. So again, all of these solutions are viable solutions. They just may not make sense to have a transport direction in an opposite way of what is common knowledge for the area. That you could represent a number of different types of solutions to show a range in transport processes at the site. And finally, you can download the image, or you can just right-click on it and save the picture as you would like. And that is a quick summary of this method. And if anyone has any questions or comments, we'd love to hear them at this time, or ideas for work to improve this method, or any of our settlement budget tools that Ashley reviewed. one of the things we are talking about doing is, as we kind of alluded to in the beginning, is combining these tools so that the sediment budget analysis system with the cells, the red and the green and the blue cells, you could take this kind of a solution and populate it or put it into a traditional cell and flux format of SBAS so that you could look at it in that format also besides just having the spaghetti line figure. Does anyone have any questions or comments? All right, well, we'll go ahead and let you all go, and thank you for your participation today. And please feel free to email either me, Mitch, or Ashley if you have any thoughts or ideas for future work in this area.